Hi everybody. Today I'm going to talk to you about simple harmonic oscillation, and specifically pendulums. We've talked a lot about pendulums in class, if we're going to be honest. We've done a bunch of experiments with them, and this will probably be the last one. But I just wanted to kind of touch base with you on it because this is going to help us to get a definition of this concept, which is called simple harmonic oscillation, which is important for waves. Now, you know how a pendulum works. A pendulum, initially, it's on a string, and there's a mass of some kind at the end of the string. And then someone does work to lift the mass to a certain height. And so you can see where that height is right there. So work is done to lift it up. And that work, work goes into the system. And as a result, we know that that work becomes potential energy. And in this case, it's specifically gravitational potential energy. And then as the pendulum is allowed to swing back toward its rest position, it converts that gravitational potential energy back into kinetic energy. And then as it has so much kinetic energy, it can't stop due to its inertia at its rest position. It overshoots the rest position and then moves its way past to a higher point again. And as it moves its way up through that, the remainder of its circular path, it converts this kinetic energy back into gravitational potential energy. So hopefully that makes sense. So it kind of oscillates back and forth between the conversion for gravitational potential and kinetic energy. We saw this in springs as when I first hooked a mass onto a spring that I hung from the ceiling. It found its equilibrium position when the spring force and the gravitational force were balanced out. I could then do work on it. As you recall, I took the bob and I pulled it down, and therefore I did work on it, and that work became potential energy in the system, specifically elastic potential energy or spring potential energy. And then as I let that go, the spring potential energy was converted to kinetic energy as the spring snapped back towards its rest position. That kinetic energy then caused it to overshoot that rest position and go higher than it normally would be, as a result gaining back potential energy. And so it exchanged potential energy for kinetic energy for potential energy and so on. All the time, though, I think you'll recall that the total energy in the system, which was equal to the amount of work that you put in, was either split between the kinetic and potential energies, or through damping and through friction into thermal energy. And so over time, as you might recall, this amount goes down and this amount here goes up, but the total energy in the system remains the same because that's we can assume over a short period of time that it's a relatively closed system. So the same thing happens here. Here we have two forces that are interacting, and it's the interaction of those two forces that cause the oscillation to occur. Here we have the same thing, only it's a little more complicated because the gravitational force that's acting on a pendulum bob and the tension force that's acting on the string are not in the same dimension. So we have to use two-dimensional vector addition to be able to analyze this. And so here if you recall, I've used the parallelogram method to add these two vectors together. And so you can see that there is a net force that acts towards the rest position. That's that green force right there. And so that's what's causing the pendulum to oscillate back and forth, because there's a net force. Here the net force is towards the rest position, and here the net force is towards the rest position. And so you can see that the net force is the thing that's causing it to oscillate back and forth. It's the thing that's causing it to change from potential energy to kinetic, and from kinetic back into potential. If you have a system in which the total energy over a period of time, the total energy is only split between the kinetic and potential energies, you have what we call a simple harmonic oscillator. So simple harmonic oscillators are objects that oscillate with the exact same motion or range of motion over a period of time. And they don't really lose to thermal energy. Now, is this a real-world pendulum? Would we ever find a real-world pendulum that's like this, so that once we set it in motion, it stayed in motion forever? The answer is no. In fact, if you have a pendulum, like a grandfather clock, for example, a grandfather clock has a mechanism at the top here that causes a little bit of a push to be given to the arm of the pendulum that keeps it moving. So it gives it a little bit of a kick every time it swings over. That's why you have to wind pendulum clocks pretty often, because the mechanical energy that's used to do that little bit of work to kick the pendulum has to come from someplace, and so usually it comes from some sort of stored energy that you've put into the system when you wound the clock. And so that's what keeps it going. Over time, though, if you let it go, if you don't wind the clock, it will run down, and it will stop keeping time anymore. So simple harmonic oscillators are oscillators that don't experience anything called damping. Damping is the friction that decreases the amount of mechanical energy in the system. And so over a short period of time, we can pretend that a real-world pendulum is a simple harmonic oscillator. We could also, I think we did this in class, pretend that a spring pendulum is a simple harmonic oscillator over a short period of time, because the amount of damping that it experiences is very small. Does it actually happen in the real world? Not really that often. There are a certain set of circumstances that come pretty close to simple harmonic oscillation, and we'll talk about those as we get closer to waves. One last thing, you might remember that for a spring over here, the formula to figure out the period of the spring, and that is the amount of time that it takes to oscillate through one full complete oscillation, was this formula 2 pi times the square root of m over k. So m is the mass of the pendulum, the spring pendulum bob here, and it's the thing that resists a change in its motion. K is a description of the spring itself, and therefore a description of the spring force. And so that tells us how much time it takes for the spring to oscillate around its rest position. For a string pendulum like this, we have a similar formula, and this one's actually on your formula sheet. So if you look at the formula sheet, you'll see it's 9.1. This is the one that will actually be on the test. You have the period of a string pendulum is equal to 2 pi times the square root of the length of the pendulum. And I just want to point out that that's the distance between the axis of rotation, the pivot point, and the center of mass of the bob. That's important and will be important in the lab that we do this week, so just be careful about that. So that's the length of the pendulum, and it's analogous to the mass here because mass is the defining feature of the spring pendulum. Length is the defining feature of the string pendulum. Now, why is it length and not mass here? Well, the reality is you have to remember that the length is actually the radius of the circle that this thing is rotating through. So if you remember back to our rotation discussion, that the radius is going to be the primary descriptor there. Also, you remember that gravitation is important here, and so as a gravitational as something that's experiencing gravitation, you remember that the mass is not important for figuring out the gravitational acceleration, and so that's the other constant right there. Gravitational constant, the gravitational acceleration constant right here, this 9.81, is important because it's the description of the force. So right down here, we had K was the description of the spring force. Here we have G is the description of the gravitational force. Those are the two most important forces that are at work here in the systems. So hopefully that makes sense. Anyway, so just to wrap up here real quick, simple harmonic oscillators oscillate without much damping, without any damping, and we can pretend that we have a simple harmonic oscillator over a very short period of time. A pendulum has its own specific period formula that's very similar to a spring pendulum, but this one is a little bit more applicable for what we're doing. What's important to note, though, is that this is a constant and this is a constant, so the only thing that you can actually do to change the period of a pendulum is to change its length. And so we're going to do a lab on that later this week. Thanks for watching.